All right, so we're going to look at question 3. And question 3 asks us to consider a surface. So we're going to consider the surface S. And S is going to be defined by its height is a function of x and y, such that x cubed minus xy plus 3. And the first thing we want to do is we want to find the directional derivative at the point 0, 1. In the direction of vector v equaling 3/5, 4/5, which is already a unit vector, right? This was the same unit vector that was in the first question that we had, right? 3, 4, 5 triangle. If I go to make a unit vector out of this, let's see, the magnitude of v is going to be 9/25 plus 16/25 rooted. So that's a magnitude of 1. All right, so this is already a unit vector approach. So we can take the approach that what we need to do to get the directional derivative then is that we're going to look at the gradient at f of the 0.01. Now, I got to keep my notes on better pieces of paper here. Do these problems out and then go to talk about them. And there was question 1, question 2, here's question 3. All right, so I'm going to need first to find the gradient. So the gradient of f is going to consist of the components of the partial with respect to x, so that's 3x squared minus y, and the partial with respect to y, which is negative x. This means that our gradient of f is equal to 3x squared minus y I hat plus negative x j hat. And if we look at the gradient at the point, well, there's two ways we can look at it. We can multiply the unit vector. So let's say the gradient of f times v, which is already a unit vector because the magnitude of v is 1. Then n, we're going to have 3/5 times 3x squared minus y I hat, or I'm sorry, plus 4/5 negative x. And then if we evaluate this at a point 0, 1, then we're going to have 3/5 minus 1 plus 4/5 or 1 as our directional derivative in this case. 1 times 3/5. Sorry. Or 3/5. And so this is actually very, very, very similar in how it's behaving to question 1. All right, let's look at the second part of this then, that asks us for the equation for the tangent plane to the surface. The equation for the tangent plane, what we can do is we can look at the point itself and work on how this point is related to our function here. So we have a surface, and the surface our surface is changing, and so a tangent plane is going to be at any of the critical points. Will be the let me get my words correct. The tangent plane is orthogonal to the gradient. So the gradient vector at the point. What we want to look at then is that our first derivative of x at our point in question minus or times x minus x naught plus our first derivative in y at the point y minus y naught minus z minus z naught. And this gives us the value. So we found our f of x here. So we'll evaluate f of x at the point 0, 1, and that's going to give us negative 1 times x minus 0 plus 0 for the y portion of it, right? Because this zeroes out the whole y portion. Minus, and now we're going to have z minus z naught. Well, to find z naught, we come back up here and we plop in 0 and 1. And so we're going to get 0 cubed minus 0 times 1 plus 3, or we get 3. And if we put this all together, then our tangent plane is going to be negative x minus z plus 3 equals 0 for this surface. And so the tangent plane is here, or we have a plane defined by the normal of negative 1, 0, negative 1, and it passes through.